Okay, now we're going to look at another way we can use differentiation to solve inequalities that involve either algebra mixed with trig, or algebra mixed with logs, or algebra mixed with exponentials. Okay, so this method is broader than the first method. This method is pretty much encapsulates the first method. The first method relied on the function increasing over the domain, which is a very specific type of function. So the first method involved the function had to increase over the domain, so we just had to check the initial value. But for this particular method, maybe the function doesn't increase over the particular domain. And this method hinges on the fact of finding global minimum. So if a question asks us to show that a function is greater than or equal to 0 for some particular domain, we show the global minimum for that particular domain is greater than or equal to 0. So by showing that the global minimum value is greater than or equal to 0, we're showing that the lowest value is greater than or equal to 0, so therefore the whole function must be greater than or equal to 0. If the lowest value is greater than or equal to 0, the whole function must be greater than or equal to 0. Okay, so visually you can sort of see that this is some sort of function here. You don't need to know how to graph the function, but the key thing is that if you can work out the global min here, so imagine the global min here is at, I don't know, some point CD. Because I know the global min is at the point CD, global min at some point CD, I can say the whole function will be greater than or equal to the y value there. So therefore f of x is greater than or equal to d for the domain. So this particular bit at the bottom here is just a recap on how to find global max and min. Basically, you're looking for stationary, to summarize, you're looking for stationary points and endpoints. Okay, so find all points where f dash is equal to 0 or is undefined. So undefined, that might be an absolute value or something like that. That could be a minimum value. But that's rare, by the way. Undefined is very rare. F dash is equal to 0. We're looking for stationary points. As always, you must always test your stationary point if it's a local max or min. So second derivative test or first derivative test, table of slopes. So that's stationary points. So this bit here is all about stationary points. And then step 2 is all about evaluating the function, so working out the y values for the stationary points and the endpoints. And from this we can identify the global max and min, but the key thing we want here is the min. We care about the min. We're trying to show that the function is greater than or equal to 0, so we care about the min value. Okay, if the function is continuous and there is one local minimum turning point in an interval, it must be the global, just cross out that maximum, it must be the global minimum, and there's no need to test endpoints. So this special note is for the case of one minimum turning point. If you've got a continuous function, and there's one stationary point, it's a minimum, then that minimum will be the global minimum. Okay, and you should be used to writing a particular statement to prove that, and you would have learned that in 2 unit. But we'll go through an example where we write that particular statement. Now, let's do this example. So prove that x minus 1 greater than or equal to ln x for x greater than 0. So you could probably graph this and almost convince yourself from the graph, I think. So x minus 1, that looks something like this. And we know our ln graph looks something like, I'll try and redraw that. Crosses there. So that's y equal x minus 1, that's y equal ln x. So you can sort of see it from the graph, what's going on. Maybe you're not convinced here though, but hopefully you know that x minus 1 is a tangent to ln x when x is 1. So it'll be okay. So we can almost see it from graphically, but let's prove it concretely using calculus. So I'm gonna set a function. I'm gonna let f of x be left hand side minus right hand side. So x minus 1 minus ln x for x greater than 0. Okay, so the key thing is I want to show that this f of x is greater than or equal to 0. Okay, so the key thing I care about is the minimum of this particular function. So let's first do the first derivative. So it's going to be 1 minus 1 over x. And let's now think about this particular expression. Interesting that if say x was equal to a half, you would get f dash of a half being 1 minus 1 over a half, which is 1 minus 2, which is negative 1. So you can see this doesn't work with the previous method because there are negative values of f dash. So this f dash isn't positive for the whole domain. So therefore the function is not necessarily increasing throughout the domain. Okay, so so that means that we need to go about this using method 2. So we're looking for the global min. So we're going to try and find stationary points. So we're going to look for stationary point, set f dash equal to 0. So 0 equals 1 minus 1 over x. Let's bring that guy over. So x is going to be equal to 1. Okay, I might just quickly work out f of 1. So subbing in 1 there, you're going to get, this is 0. Well, I should definitely hope that this is the minimum value, because if we have anything lower than 0, we're in trouble. Okay, so that's, so therefore stationary point at 1, 0, but let's test the nature. Now, I think it's easy enough to work out a second derivative, so I'm going to do that. But first, the first derivative I'm going to rewrite with x to negative 1 there, that 1 over x is x to negative 1, so it makes it easier to find the second derivative. So I can do a second derivative test for that stationary point. That's going to be bringing down the negative 1, that's going to be 1, and then taking away 1 from the power, negative 2, so that's 1 on x squared. So f double dash x is 1 on x squared. Let's substitute in 1 into f double dash, so we get 1 on 1 squared, or 1 on 1, which equals 1, greater than 0. We're greater than 0, so we're a smiley face. So therefore, we've got the point 1, 0 is a local minimum turning point. Okay, so in this particular domain, we've got one turning point, and it's a local minimum. Now remember that we need to say about global minimum, and remember that because we've worked out that there's only one turning point in the domain, that local minimum will be the global minimum. Remember that from your 2-unit work that we need to now write down a particular quote. Now your other classes might use very, very slightly different wording, but this is the wording that I've used with my class. So since f of x is continuous and has only one turning point in its domain, and I might just quote the domain, x greater than 0, the local minimum is the global minimum. So therefore we know that there's a global minimum at the point 1, 0. So therefore we can say that our f of x is greater than or equal to the y value here of our local minimum turning point, which is 0. So f of x is greater than or equal to 0, and now I'll just substitute in for f of x 1. X minus 1 minus ln x is greater than or equal to 0. and let's just adjust. We get 1 minus x is greater than or equal to ln x as required. Okay, there you go. See you next video for the next example.